So we're going to talk about solving equations involving logarithms, which definitely still uses our properties of logs and also uses the fact that logs and exponentials are inverse functions. It's a little bit easier to undo a logarithm, mostly because in our calculator we always have the inverse right away. So for example, log base 5 of x equals 2 means that I raise 5 to the power of 2 and it gives me x. So I can just use the definition of logarithm to say that x must be 25. I could also solve this thinking of the exponentials as inverses and say if log base 5 of x is equal to 2, then 5 to the log base 5 of x is equal to 5 squared, or x is equal to 5 squared. So x is 25. The reason why it's a little bit easier than solving exponentials is because I'm not limited to just two, like natural log and log base 10, because every base I can plug into my calculator. But with logs, I usually only have log base e or log base 10. But I can always take 5 to a power, or 10 to a power, or e to a power. Any of those are already in my calculator. So similar thing, if I have natural log of x equals 2, I need to remember that natural log of x is log base e. So that means if my exponent is 2 on e, then x is e squared. And that's some number that I can use my calculator to find. Those are the very basic equations. But I could solve something more complicated, like if I wanted to know when a logarithmic function outputted 0. So the x-intercepts of this logarithmic function, maybe. So what I would do is I would isolate the logarithm. That would be my first step. So if I have natural log of 3x plus 2 minus 5 is 0, to isolate the logarithm, what I need to do is add 5 to both sides. So then I get natural log of 3x plus 2 is equal to 5. And now I use the fact that natural log and e are inverse functions to say 3x plus 2 is e to the 5th. And now I can just solve for x like I'm used to. Subtract 2 from both sides. So you get 3x equals e to the 5th minus 2. Divide both sides by 3. So I get x is equal to e to the 5th minus 2 over 3. And I've solved that logarithmic equation. Now, if I have a logarithmic equation involving more than one log, I can still solve it as long as they're the same base by using the property of logarithms to condense it into a single logarithm. So for example, if I have log base 4 of 3x plus 5 minus log base 4 of 2x, I can condense that into a single logarithm using the property of logs that says the difference of these is a ratio inside the logarithm. And now I have log base 4 of 3x plus 5 over 2x is equal to 3. Well, that means if I take 4 to the third power, so it's like I'm thinking of doing the inverse on both sides of this equation. If I take 4 to the third power, I should get 3x plus 5 over 2x. 4 to the third power, well, that's 16 times 4 is 64. And now I can solve this just using the tools I already have. I multiply both sides by 2x. This is a rational equation. So I get 3x plus 5 is equal to 128x. Subtract 5 from both sides. Actually, that's not what I would want to do. I would want to subtract 3x from both sides. 5 is equal to 125x. And so x is equal to 5 over 125. Or 1/25. And that's my solution. With logarithms, I do need to sometimes check that my solutions work. If I only find one solution, then it is fine. But sometimes if I have a quadratic that I solve instead of a rational function right here, I'll pick up extra solutions and I'll check and make sure that they work inside the logarithm. So let me show you how that works in the next problem. So if I'm going to solve log x plus log of x plus 3 equals 1, I'll use the property of logs to say that that's the same as log of x times x plus 3 is equal to 1. Now you can see how I'm going to pick up a quadratic. Well, let's first undo the log. So common log is log base 10. So I would raise both sides to the power of 10, or 10 to the power of both sides, and I would get x times x plus 3 is equal to 10 to the 1. That means x times x plus 3 is equal to 10. And this is a quadratic. Now, if you remember with quadratics, you always want to put them in standard form. That way I can either factor or use the quadratic formula to simplify. So standard form looks like multiplying out and subtracting the constant so that it's equal to 0. So you want to get the quadratic all on one side and 0 on the other side. Once I'm in standard form, then I can either factor or I can always use the quadratic formula. Let's see if we can factor this one. So I need something that adds to 3 and multiplies to -10. So if I add 5 and take away 2, I'll get 3, and I'll also multiply to -10. So either x minus 2 is 0, or x is 2, or x plus 5 is 0, and x is -5. And this is where I need to check. So if I check my solutions, if I do the common log of 2 plus the common log of 5, then that's going to be the common log, so that 5 is coming from 2 plus 3. That's going to be the common log of 2 times 5, or common log of 10. And the common log of 10 is just the exponent 1. Because that's what I raised 10 to give me 10. I raise it to the power of 1. So that totally works. But if I also check -5, I see that there's no power I can raise 10 to give me -5. This is undefined. So we say x equals -5 is an extraneous solution, and my only solution here is x equals 2. So with logarithms, just like with rational functions, you want to check and weed out any extraneous solutions. With rational functions, you weeded out anything that made the denominator 0. With logs, you weed out anything that would make whatever's inside the log negative, because you can't raise something to a power and get a negative number. So I would suggest that you pause the video and you try this next equation and see how it goes. So hopefully you paused the video and you tried it, and hopefully your first step was to isolate the logarithm. So if I have 1/2 log of x minus 1 plus 1 equals 3, if I subtract 1 from both sides, I get 1/2 log of x minus 1 is 2. If I multiply both sides by 2, I get log of x minus 1 is 4. This is the common log. So I would do 10 to the power on both sides. And so I get x minus 1 is 10 to the 4. And then I would add 1 to both sides of the equation. So I get x is, what is 10 to the 4? 10,000 plus 1. So 10,001 would be my solution. And I could double check and make sure that this works. So 1/2 log of 10,001 minus 1 plus 1 is 1/2 common log of 10,000 plus 1 is 1/2 common log of 10,000 is 4. I get 2 plus 1, which is 3. So there's several examples of solving logarithms, or equations involving logarithms.